Today, we're diving into a story that's about way more than just medicine. It's a story about our own DNA, about a wild twist of evolution, and about how one single microscopic typo in our genetic code can change millions of lives. This is the incredible global story of sickle cell anemia.
To really understand sickle cell, you have to start with what it feels like. And a medical journal once put it with this brutal honesty that just cuts right to the heart of it all. More than anything else, sickle cell is a disease defined by pain.
And look, we're not talking about a dull ache here. People who live with this describe the pain crises as a feeling of their bones literally bursting from the inside out. It's this all-consuming, crushing feeling that can go on for days or even weeks, just unimaginable. So you have to wonder, right? What on earth could cause something that severe? It's not a virus, it's not an injury. The answer is something way, way smaller, hidden deep inside our genetic blueprint. The cause of all this is a single letter. Okay, so to find that one letter, we need to zoom in on a little protein called hemoglobin. The easiest way to think about hemoglobin is like an oxygen taxi service inside your red blood cells. Its whole job is to pick up oxygen from your lungs and deliver it to every single cell in your body. It's kind of important. And this is where it gets mind-blowing. In a normal hemoglobin protein, at the 6th position, there's an amino acid called glutamate. In sickle hemoglobin, that one single amino acid gets swapped for another one called valine. That's it. That's the entire problem. One tiny substitution out of hundreds kicks off this whole devastating disease. So, how does this get passed down? Well, it happens when two parents are what we call carriers. They each have one normal gene and one sickle gene, but they're perfectly healthy, they have no symptoms, and they might not even know they carry it. But for every single pregnancy, there's a 1 in 4 chance that their child inherits both sickle genes and is born with the disease. But that one tiny genetic typo doesn't just stay put at the molecular level. Oh no, it sets off this huge, destructive chain reaction, a cascade of effects that ripples through the entire body. All right, so let's start with a baseline, a normal, healthy red blood cell. It's supposed to live for about 120 days, 4 months. It cruises around, delivers its oxygen, and then gets recycled. Simple, efficient, no big deal. Now look at this. A red blood cell with sickle hemoglobin lives for maybe 20 days. Sometimes it's as few as 10. They're just so fragile, they break apart and die off way, way too fast. And when your body is constantly short on red blood cells, well, that's what we call chronic anemia. But it actually gets worse. When these mutated cells drop off their oxygen, that single amino acid swap causes all the hemoglobin inside to stick together, forming these long, hard rods. This forces the cell to change shape from a nice round disc to a hard, sticky crescent, a sickle. And you can probably guess what happens next. These stiff, pointy cells can't squeeze through tiny blood vessels. They get stuck. They cause log jams, basically massive traffic jams on a cellular level. And those traffic jams, that's the disease. That's what causes those pain crises. But it's also what starves your body of oxygen, leading to organ damage, a huge risk of stroke, especially for kids, and a really dangerous lung problem called acute chest syndrome. It's a disease that just attacks the whole system. So this all brings up a really big question, right? If this gene is so harmful, why is it still around? Why didn't evolution just get rid of it? Well, the answer is fascinating, and it takes us from looking at cells under a microscope to looking at a map of the entire world. When you actually map out where sickle cell disease is most common, the pattern is just impossible to ignore. Almost 2/3 of all cases in the entire world are found in sub-Saharan Africa. You also see it a lot in parts of India, the Middle East, and around the Mediterranean. So why those specific places? This isn't random. It turns out this map is hiding the ghost of another, even older killer. And this is where the story takes a really surprising evolutionary turn. Here's the kicker. The map for sickle cell, it overlaps almost perfectly with the world's malaria belt. For thousands of years in these parts of the world, having 2 normal hemoglobin genes meant you were extremely vulnerable to malaria. Having 2 sickle cell genes meant you have the disease. But if you had one of each, if you were a carrier, you got a biological superpower. You were protected from the worst of malaria. You survived. That's the heterozygote advantage, and it's the only reason this gene has stuck around. So for centuries, that was the story, a painful genetic disorder born from an evolutionary trade-off. But the story is changing. For the last 100 years or so, science has been in a full-on fight with this disease, and we've gone from just observing it to managing it, and now, finally, to actually curing it. And the way we treat it has completely transformed. It starts with daily management, pain relief, hydration, avoiding triggers. Then came drugs like hydroxyurea, which was a true game changer in reducing those awful pain crises. A bone marrow transplant can be a cure, but it's risky and you need a perfectly matched donor. And now we're in a whole new world. We're talking about gene therapy, literally going in and fixing that original typo in a patient's own cells. I mean, just look at this journey. In 1910, a doctor just saw some weird-looking cells. By 1949, we knew the exact molecule responsible. It took all the way until 1995 for the first major treatment to be approved. And now, just in the last year, the first gene therapies are here. The pace of discovery is it's breathtaking. So we end here at this incredible moment. For the first time in human history, we can honestly say that a cure for sickle cell anemia exists. The science has delivered. But now the biggest challenge isn't in the lab anymore. It's in the real world. These new therapies are incredibly complex and unbelievably expensive. So the final question, the one we're all facing now is, now that we have a cure, how do we get it to the millions of people who need it most?